Let's see. So we were talking about ultrafiltration, and I think we got about up to here. So I was talking about how the yes, I talked about tangential flow filtration. Device is more complicated since conversion of feed flow rate into filtrate creates nonlinear pressure drop on the retentate side, and I explained that, right, because you have this pressure profile of decreasing pressure on the feed side from the feed to the retentate, right? Let me show that again, and then we can start from that point. And, oh, thank you. So what I said was, that basically if we look at a membrane like this, we have a permeate side pressure, and we have a feed pressure here, we have a retentate pressure, and typically the pressure drops like this. The permeate side pressure is approximately constant, right? It's also going to drop a little bit if you're flowing that way, it's approximately constant. But the transmembrane pressure drop here will be different to here, and we usually use an average. But that's okay, but the fact is that if it's going to vary like that, then the permeate flux is different at various points, you get different amounts of fouling, and so that's why it depends non-linearly. That's where this comment comes in, that the pressure drop on the retention side of the module is much more complicated. The measured permeability scales the reciprocal of solution viscosity. We talked about that. Okay, so protein retention and ultrafiltration is assumed to be purely size exclusion, but I mentioned also you can actually enhance this separation by having surface effects, whether it's different charge species, hydrophobic interactions, so forth. Nominal molecular weight cutoff provides a minimal information on product retention. This is important since membranes with the same molecular weight cutoff but different pore size distributions can have very different behavior at the 99% retention level needed for ultrafiltration and diafiltration processes. So I think we talked about this earlier, that we don't know what the minimum pore size is or the maximum pore size, but we have different pore size distributions. And typically, these pore size distributions look something like this. So typically they look something, I'm exaggerating here, like that. So this might be the modal size, and you have, often it's modeled like this as a log normal distribution where you have a very long tail here, and here, of course, it can't go beyond 0, right? Sometimes people try to approximate it as a normal distribution, but the fact is that you can have different pore size distributions that give you the same rejection, right? Because it really depends on how many of these small pores and big pores you have as to what actually happens when you look at rejection. And so that's why when you say something has a nominal molecular weight cutoff, it really doesn't tell you a whole lot. It's a minimal amount of information, right? So if I'm going to do a BSA filtration, I want to reject BSA, for example. BSA molecular weight is what, around 70 kilodalton, something like this. So if I use a nominal molecular weight cutoff of about 60 kilodalton, I'm expecting to get a reasonable rejection. But looking at different 60 kilodalton membranes, I might find different rejections. So one might give me 85%, one might give 95%, it depends. Again, these nominal molecular weight cutoffs that the membrane manufacturers give you are for their particular membrane under a certain set of conditions that they have chosen for a certain species, typically dextran. Okay, people typically use dextrans because they are globular, so that if you have a long molecule like DNA, then that actually might go through a small pore size membrane because it can elongate, right? But dextran is globular, and the other thing about it is dextran tends to be not very fouling. You don't want a species that goes and adsorbs on the membrane surface. That will give you a different rejection profile. So again, when you have nominal molecular weight cutoffs and you're thinking about this, remember, it doesn't mean that you should get exactly that. You will get something in that range, okay? Charged proteins in electrolyte solutions surrounded by diffuse ion cloud or electrical double layer due to electrostatic interactions with the counter and co-ions can have different rejection properties. And so, whoops, I'm sorry. Let me try and get my pointer back. Okay, so if the electrolyte is surrounded by a diffuse cloud of electrical double layer and counter ions, it's actually bigger, right? And so the rejection might be different again. And proteins are charged, and so their size in a liquid depends upon buffer conditions, all right? So some buffer conditions, the hydrodynamic radius can be smaller, it can be bigger. This can have a big effect on rejection. Effective size of protein is increased by the presence of this diffuse electrical double layer. Additional electrostatic interactions arise from an increase in free energy associated with distortion of the double layer adjacent to the pore wall, and direct charge-charge interactions between the charged protein and the charged groups on the membrane surface. These effects can be quite dramatic, and there's a lot of literature today about, if you like, advanced ultrafiltration processes where you're making use of these additional factors to tailor the separation, to tune the separation you get. Okay, so if we talk about mass transfer, filtrate flux in tangential flow ultrafiltration is typically governed by concentration polarization effects, which are commonly described using a classical stagnant film model. So we've talked already about concentration polarization. The stagnant film model, this model just assumes that basically here is my membrane, and then I have a permeate flux going through, so I have convection here, and then I have back migration, and you get some sort of concentration variation in this way of your protein. It decreases as you go away from the membrane, increases as you get to the membrane surface. Similar to microfiltration, except in the case of proteins, they are actually dissolved species, right? So you won't get a cake layer form because they're dissolved. Okay, so concentration polarization means a higher concentration near the surface, but they dissolve. Now, there is a phenomenon known as gel formation, because the hypothesis here is, or was, that as the concentration increases near the membrane surface, you will reach some concentration where the protein is no longer stable and starts to precipitate. That was the hypothesis. However, if you do calculations and try to estimate this gel concentration, it's often much higher than the solubility limit. So it's not really a precipitation, it's more some sort of very concentrated layer near the surface that is a very high viscosity and basically has a resistance to mass transfer. So if you use this sort of model, you can do a mass balance of what comes towards the membrane, what goes away from the membrane, can integrate, and you end up with an expression like this that tells you the flux is equal to Cw is the concentration at the wall, at the surface of the membrane, and then Cb is the bulk concentration somewhere in the bulk, and then you have a Cf, and so Cf is the concentration that you're working with. So basically, I give them all here: bulk concentration in the filtrate and at the wall. So these are your three concentrations. Now, if you have total rejection of your protein, Cf is obviously going to be 0, right, in the filtrate. Sometimes you only have partial rejection. K is called a mass transfer coefficient, right? And in this case, it looks as if it's some sort of proportionality constant. But mass transfer coefficients can then be given by mass transfer correlations, okay, which probably some of you have come across in the past. So mass transfer coefficient is a function of device geometry, hydrodynamics, protein diffusion coefficient. Protein diffusion coefficients in turn depend on protein charge, isoelectric point and pH, buffer conductivity, and protein concentration. So the mass transfer coefficient is a lumped parameter approach that basically, if you like, tries to describe the rate of mass transfer in this process. And so if you think of a fundamental mechanism, then mass transfer coefficient must somehow be a function of the protein diffusion coefficient, right? Because diffusion is what's causing movement of this. There's also convection and other things. But anyway, diffusion is important here, okay? The diffusion coefficient, as I say here, is a function of concentration and various other things. And so ultimately, concentration, conductivity affect the rate of mass transfer, okay? These effects can be quite pronounced, with the mass transfer coefficient varying by as much as a factor of 2 in different buffers due to differences in protein charge, intermolecular electrostatic interactions. So that is why in the biotech industry, choice of buffer is very important. The buffer can lead to protein precipitation if you have the wrong sort of buffer, but it is also very important for trying to maximize mass transfer. Okay? The diffusion coefficient is also proportional to absolute temperature and inversely proportional to viscosity, and viscosity is a strong function of temperature. Oops, I'm sorry. So the diffusion coefficient is also proportional to absolute temperature and inversely proportional to viscosity, right? So, which is itself a strong function of temperature. So you know that if the viscosity goes up, the diffusion coefficient goes down. If the temperature goes up, the viscosity goes down, okay? And the protein diffusion coefficient goes up. Typically, viscosity has a very pronounced effect because if you're working with higher protein concentrations, you'll find that the viscosity increases quite a bit, all right? Temperature is important. So generally in biotech operations, the preference at one time used to be to run at 4 degrees Celsius because it was felt by that running at 4 degrees Celsius, you minimize the risk of any sort of infection and so forth. There is, however, a movement today to run at 20 degrees Celsius. Whatever it is, it's going to be a controlled temperature. But there are various advantages running at 20 degrees Celsius, one of which is that the viscosity is going to be lower and your processing is easier, okay? And so both temperatures are used today, actually. So this can result in the increase in mass transfer coefficient, hence filtrate flux at higher operating temperatures. At constant feed flow rate and high conversion ratios, filtrate rate to feed flow rate, mass transfer coefficient will decrease along the length of the module due to a reduction in retentate flow rate. So all that was saying is something I had said earlier, which is that if you have high conversion ratios, right? So your feed is coming along here, and a large amount of it is decreasing as permeate, then a Q here is going to be much less, right? So you have much less feed. And so the velocity changes and so forth, and so all this is telling you is that if you have these conditions, then there's going to be a change in the mass transfer coefficient. I also mentioned earlier that if you have longer modules, right, the overall flux is lower for the same reason. The protein concentration of the membrane surface increases with increasing filtrate flux, that makes sense, which may result in increase in protein transmission. Now, that's something else we didn't talk about. So, typically, we talk about a rejection coefficient for this membrane. So, this membrane, we could say, has a rejection coefficient of 0.9, which means it's rejecting 90% of BSA under your operating conditions, okay? But that rejection basically is comparing the concentration here at the membrane surface, the wall, versus the concentration in the filtrate, okay? Now, what you measure, though, is the concentration in the bulk feed, right? You can't measure a wall concentration. So you may see a drop in the rejection coefficient, but that's an apparent rejection coefficient because rejection really depends on what it sees on either side of the membrane, okay? And so that's what is meant by, for more concentrated solutions, you may actually see a drop in rejection, an apparent drop, because if you have higher wall concentrations, you're going to have more protein passage. Because if the rejection coefficient is constant, you'll still have more protein passage than you expect. Osmotic pressure increases, thereby reducing the effective pressure driving force. Osmotic pressure effects are very, very minor in microfiltration. They are a little more important in ultrafiltration. They are very important in reverse osmosis, okay? Okay. There is often a critical transmembrane pressure known as the pressure-independent flux. Let me explain that. Oh, I need to move this on, sorry. Okay, so what's meant by pressure-independent flux? Okay, so I pointed out that if you consider your membrane here, you have the feed coming this way and you have a permeate flow here, right? And so if you look at what's happening here, you get a build-up here and a concentration polarization boundary layer. And at some point, you'll end up in some sort of pseudo-steady state because you're pumping at a certain rate here. It's a narrowing of the channel, but that leads to dragging away of this material, and there's back migration, and this is somewhat pseudo-steady, okay? And so you could say that if you've got flux versus pressure, so you're somewhere here, say, okay? And then I increase this driving force, say I double it, and so then what happens? I'm increasing the pressure drop, and the flux goes up somewhat, right? Because I'm increasing the amount I'm pulling through here. So what does that do? That causes this concentration boundary layer and the deposited material to increase, but then I'm starting to pump faster here, but there's an overall increase. Now, at some point, as I keep doing this, you're not going to get an increase in flux, because what will happen is that may cause an increase in this layer here, but then you get a higher flow rate, which causes a decrease, and so really there's no change, and you get to this so-called pressure-independent operation. So further increases in pressure will not lead to an increase in flux. Actually, that's so these curves typically do something like this. Is a linear region, and then it typically curves off like that. But operating in this region is quite dangerous, because what happens is you can have big increases in pressure that only lead to very minor increases in flux. But big increases in pressure can cause more membrane fouling, can cause more irreversible fouling, can cause damage to proteins. So ultimately, you may see a decrease in flux. Okay? So operating in this pressure-independent region is very dangerous. So you really want to operate in this range here, where you know that a change in pressure leads to a big change in flux, so you can control this much more carefully. In the pressure-independent region, that's difficult to control. Where was this? High protein concentration can reduce membrane permeability through irreversible fouling or through formation of a gel layer or cake layer on the membrane surface. We don't really have cake so much, we talk about gels. In this case, the pressure-independent flux is determined by protein solubility or gel concentration as it compared to microfiltration. You have a pressure-independent region for microfiltration as well, but there it's due to cake formation. Okay? Okay. Oops. Next, let's see what we have here. Okay, so types of membranes. So flat sheet membranes are cast from a variety of polymers. Actually, they are somewhat similar to the ones that we mentioned for microfiltration, right? Polysulfone, polyether sulfone, regenerated cellulose. The membranes are similar. But they all have an asymmetric skin structure, a thin skin to provide the desired selective layer, while a most porous substructure to provide mechanical support. In microfiltration membranes, they could be asymmetric, they may not be, but often you don't have these barrier layers that are made of a different material. You can in ultrafiltration. Synthetic polymers have high thermal stability, chemical resistance, allowing use of fairly harsh cleaning chemicals. Regenerated cellulose is actually a nice polymer because it's very hydrophilic. It reduces protein adsorption and fouling, but it is less stable to big pH swings. And so cleaning is difficult with regenerated cellulose membranes. You've got to be much milder conditions. New composite regenerated cellulose membranes have excellent mechanical strength and cause very little fouling, providing higher flux and better retention characteristics than other membrane chemistries. And so here are some examples of these membranes. The top one, A, is a regenerated cellulose membrane, and the B is a composite regenerated cellulose membrane, which has got defect-free layer with strong bond between the cellulose ultrafiltration layer and the polypropylene microporous support. So the first one is just regenerated cellulose, and the second one is a composite membrane. Okay, and there are two layers, and it is important that the two layers are bond strong together. Otherwise, if they separate, then your ultrafiltration membrane is gone. Okay. What you can, well, you may not be able to see it so clearly in this one, but ultrafiltration membranes do tend to, this is clearer here, they do tend to have large open areas here called macrovoids, okay? So we want to avoid macrovoids because macrovoids can lead to basically lower ejection. But if the macrovoids are kind of self-contained, if they're not linked with either the outside layer, the filtration layer, they're probably okay, right? In virus filtration membranes, we try to avoid macrovoids completely, and we'll talk about that later. But just see here, there are sometimes macrovoids, okay? So you can also have hollow fibers. They are made from similar proteins as flat sheet membranes. They are self-supporting and can be cleaned by backflushing. So backflushing means if you have the fiber, you pump in the opposite direction. So you are pumping, instead of pumping where the feed and the permeate comes out, you now pump from the permeate side and push in the opposite direction. Okay. This is particularly nice with hollow fibers to do this because if this is your, oops, what happened? If this is your membrane, you're pumping this way with the feed coming out. With backflushing, you pump back in this way. And so the idea is you try and release anything that's adsorbed and you remove it on the feed side. There's no need for spacers or multiple sealing procedures in hollow fibers, which reduces cost, but a lack of spacers also increases mass transfer. So in hollow fibers, you have these self-supporting hollow fibers, and you have many of them like this in a module, right? If you use a flat sheet membrane, you may have one membrane sheet like this, and then you have another membrane sheet like that, and then in between them you have to have a spacer. So this is our spacer layer that goes in between, because you don't want these two membrane sheets to collapse on each other. Okay, your feed will come through here, and you can withdraw permeate from here and permeate from here, and then typically you have another membrane layer on top of this and a feed coming here with another membrane on top of that, and then permeate from this one comes in there. So you have alternating feed channels and permeate channels. Okay, in between these feed and permeate channels you must have a spacer, otherwise the two membrane layers will touch and this won't work. The spacer takes up space, and that's why they have a lower packing density than the hollow fibers. But the spacer will also induce mixing on the feed channel, and mixing is a good thing because it breaks up concentration polarization. So there is an advantage also, as I say here, that the lack of a spacer results in lower mass transfer coefficients for hollow fibers. Okay? Fiber breakage can be a problem. So if one of these fibers breaks, then you're going to have a direct cross flow, right, between the permeate and the feed side, and that's a major issue. Okay, so it's actually one of the big things is always to check that there are no broken fibers, which can be quite complicated if you have modules with huge numbers of fibers. Hollow fiber, flat sheet cassettes, spiral wound cartridges, tubular modules, and enhanced mass transfer devices are all different ways of making these membrane modules. Okay, so hollow fibers we talked about, flat sheet cassettes we talked about, spiral wound is used in water treatment applications, tubular modules are larger tubes that exist, and then there are also enhanced mass transfer devices. You know, people make rotating membranes, right, where you have a membrane inside a centrifuge, inside a cell that you can rotate. So that provides a pressure. There are Dean vortices, there are various things people have used to try and enhance mass transfer. Modules provide physical separation of retentate and filtrate streams, mechanical support for the membrane, high membrane packing densities, and easy access for cleaning and replacement, and good mass transfer characteristics. So when you design your module, these are things you're trying to do. Okay? You want to provide a physical essential separation between the retentate and filtrate streams. Otherwise, you don't have any separation, right? You want mechanical support for the membrane, otherwise the membrane will break. You want high packing densities, otherwise you can't really process a lot of material, and you do need easy access for cleaning. Oops, have I got stuck again? Sorry. So you do need easy access for cleaning, okay? And you get good mass transfer characteristics. So, but if you think about it, you can, there's a trade-off here, because you can design very fancy modules that enhance mass transfer, but they may not be economically viable. They may be very difficult to make. You can't automate them, and so it's useless. And so that's why module design tends to be simply hollow fibers, tubular membranes, flat sheet membranes. We don't have, a spiral wound is not that common, but we don't have curled membranes like this where you induce Dean vortices and things, mainly because they work very well, but they can't be commercialized and made at large scale and large throughput. What do I say here? Spiral wound modules are subject to plugging and are more difficult to clean and have a more limited range of scalability than hollow fiber modules. Flat sheet, rotating Dean vortexes systems have been developed for ultrafiltration. These rotating and Dean vortex systems, well, there are some, but they're not that popular, mainly because they're difficult to make, and so then they become expensive, and then it's really not worth it. These devices have high mass transfer coefficients but low packing densities, and they can be difficult to scale up, scale down due to changes in hydrodynamic conditions. So linear scaling involves keeping the pressure, fluid flow, concentration profile along the length of the filtration module constant. Okay? So you want to keep constant basically the performance of the device. So the pressure drop, the fluid flow, concentration profile along the length of the module. Keep channel length constant, area changed by increasing or decreasing the number of fibers or parallel channels. So this is an example of these flat sheet modules, and you can see there, this is from Millipore. So you can have this, this rather big cartridge here. See, so this is rather a big cartridge, and you can keep stacking more and more on top of these. So you can actually They come in a stainless steel holder which has got screws that you can screw in there, and you can stack more on these on top of each other. And all they're doing is increasing the number of flow channels. Okay, this is the same one again. So this is one, and that's one. And then there are these smaller ones which are just got a smaller surface area. And so they are very modular. Okay, so they can easily be expanded or decreased depending how many you need. And so they're actually very nice, very easy to use. Linear scaling involves keeping, as I said here, fluid flow concentration profile along the length of the filtration module constant. Keeping channel length constant, area changed by increasing the number of these devices. Why is the channel length constant? Because I told you, longer channels give you lower mass transfer overall. So then it won't be the same performance, right? Linear flat sheet cassettes provide more than 1,000-fold scaling for ultrafiltration processes with consistent product yield and process flux. That's actually quite amazing. 1,000-fold scaling is actually very difficult to do. And so if you can do that and get reproducible results, that's actually very good. Okay, so now what I'd like to talk about is how we run these systems. So let me change this now and talk about this. So these are three modes of operation of ultrafiltration systems, and actually they're all used. So let's look at this one. This is the simplest one to look at. So in this one, it's in what they call, what we would call concentration mode. So here is my feed. I have a certain batch of feed I want to process, so I take it through my feed tank, I keep running around in a circle like this, and I remove the filtrate. So this is concentration. You're concentrating the protein from some value to some other value. Why do we want to do this? Because typically when you elute from a chromatography step or any of these steps, the protein concentration falls. And so at some point you've got to concentrate it. You'd also like to work with as high a protein concentration as possible because that just minimizes your volume. Okay? So this is concentration mode. We can also run this in the following mode, where here's our recycle tank. So it's the same as this one, except we have fresh feed coming in here. So we are recycling the feed, plus we're bringing in fresh feed, and then we're removing the filtrate. Okay? So that's a very similar way of operating. It's just a little different in that all of the feed is not in the recycle tank. We're bringing it in stages. And then finally, there is this thing called diafiltration. So, you know, if you want to change the buffer, supposing your protein is in a phosphate buffer, you want to change it to a citrate buffer. How are you going to do that? So, I mean, in the lab, maybe you have 1 liter, so you can say, well, I've got 1 liter of this, I can keep continuously diluting, right? I can add another liter of citrate, and now my phosphate citrate are, say, 1:1, and then I can try to concentrate it, then I can add a bit more, and so forth, right? So this is really doing the same thing, but on a continuous basis. So here's your ultrafiltration membrane, and here is the recycle tank has your feed. So you're running this in concentration mode, you're removing permeate, you're concentrating your protein here, okay? But in the meantime, you have another buffer here, this is your second buffer, that you're adding in here to the recycle tank at the same rate at which you remove filtrate. So if you add fresh buffer, not containing, say, the components you want to remove, so it doesn't contain PBS, for example, but it contains citrate, PBS is phosphate buffered saline, it doesn't contain that, then you will be continuously reducing the concentration of your phosphate buffered saline, but you will be increasing the concentration of your citrate, right? And you're doing it continuously. So that is called diafiltration. Actually, it says here, the figure gives the modes of operation used for concentration and buffer exchange diafiltration. For buffer exchange diafiltration, concentration of the component to be removed decreases as follows. So actually, it decreases as C is the concentration of the solute, C naught is the initial concentration of the solute, S is the sieving coefficient of the solute, N is the number of dia volumes. So a dia volume is a volume of the retentate here. It's a buffer volume divided by retentate volume. One dia, so supposing I have 3 liters here of feed solution I want to treat, then one dia volume is 3 liters. Okay? So it's the volume of your feed. All right? So if we assume that the sieving coefficient is 1, in other words, everything is going through, there's no rejection of what you want, and this is just an exponential decay, right? Like this. C divided by C naught versus N here, okay? That's all that is. And you have 1 dye volume, 2, 3, so forth. Okay. By the way, that's very easy to derive. So if anyone's interested in deriving it, we can do that sometime. It's very simple. It's just a mass balance on your recycle tank. Okay. You do a mass balance here. You say in minus out equals accumulation. There's nothing coming in, but you're losing your component going out. Okay. So you can then just say dC dt multiplied by V equals in, which is 0 minus what goes out, which is going to be your permeate flow rate multiplied by concentration, and you can integrate that and end up with this. And if you like, we can work that out later. If you're interested, come and see me. But anyway, what this means is that after 1 dye volume, you have lost about 67% because it's 1 divided by E. After 2 dye volumes, more than that, and so forth. And so typically people run this for about 7, 8 dye volumes till you remove about 99%. Okay? But that's very easy to model mathematically, and that's how that goes. Okay, so I think I want to talk about the problem now. So this is what we've covered so far. Going back to our scheme here, where do we find these tangential flow processes? Let me show you. Okay, so we define these tangential flow processes here typically in buffer exchange. And so buffer exchange occurs somewhere around here. It's not actually marked, but buffer exchange occurs here when you are trying to put it in your final formulation buffer, and it might be clearer here because here we have here an ultrafiltration diafiltration step. Okay. Now you may have, it doesn't show it here, you may have other concentration steps anywhere in the process, but you always tend to have one at the end because you want to put it into your final formulation buffer. Okay. So in terms of future directions for this sort of work, and we'll talk about this hopefully on Thursday, single-use devices. I mentioned that for microfiltration, also for tangential flow microfiltration, also tangential flow ultrafiltration, they're single-use devices. Continuous biomanufacturing, how would you, so, you know, in some ways, we said this is continuous, but in some ways it's not really, right? Because here's your feed tank, okay? Here is your module. Here is the permeate you're collecting, right? And then here is your diluent or buffer tank, if you're doing a diafiltration. And so you're continually adding this, taking this out. But is this truly continuous, though? Because you keep running this, you have to keep adding. If it was continuous, then your feed would be coming in here continuously, right? And so then this becomes a little bit problematic to run because you've got many passes through this, right? So if your feed is coming in here and you're running many passes through this, it's not really a one-pass system, and so making it truly continuous is a little bit tricky because you've got to match all these flow rates. And that's not that easy. I mean, a continuous system, you don't have a holding tank, right? I mean, you could get around by saying, okay, let my feed come in, stay in a holding tank, I'll take out continuously what I need, but that's not truly continuous, right? So we'll talk a little bit about what people have tried to do to make this a truly continuous process, and I'll also talk about high-performance tangential flow filtration. So that brings us to the end of this. Can we show the problem? So I have a problem now, which I think I will show you and we'll talk about a little bit. And there are two ways to solve it. So if you don't like the mathematical approach, you can try and think of a qualitative approach and tell me how you think you can solve it. And if you like the mathematical approach, there is a mathematical solution too, but it's a little bit complicated, but I think it's challenging. We can show it to them. Is there a way to email it to them, or can they? Okay. Otherwise, they can take a screenshot or, I don't know, something. Okay, and it's dealing with red blood cells. And I did that on purpose because actually towards the end of this class, we're going to talk about blood processing. So I thought, why not talk about a blood example, but it's going to use diafiltration and microfiltration. Okay, good. So I say here, a unit of red blood cells has a volume of 1,000 ml and a hematocrit of 0.15. So hematocrit, HCT, means that on a volume basis, okay, so on a volume basis, you have 15% red blood cells. So, you know, you collect blood typically in a blood bag like this, and if you were to let it all sediment, about 15% here is red blood cells. Okay, sorry, this is too small. 15% is red blood cells, and all the rest of this is going to be plasma. So plasma is basically the liquid that contains proteins. There could be some white blood cells, there could be some platelets, but about 15% is red blood cells on a volume basis. That's what hematocrit means. So it has to be concentrated to a hematocrit of 0.4. So from 15%, you want to concentrate it to 40%. Okay, so the first question is, what do you have to do? Well, red blood cells, do I give their size here? 2.6 micron. 2.6 micron, okay? So red blood cells are 2.6 micron, so you would have to use a microfiltration membrane, right? That's the best thing to do. Now, you need to remove some of the plasma. You started off with 1,000 ml. You want to end up with some new volume where this hematocrit is 40%. Okay, so you've got to remove plasma. That's okay. Now, you may assume that a feed flow rate will be chosen that results in a wall shear of 2,000 reciprocal seconds, and the hollow fibers are 10 centimeters in length. Assume an average red blood cell radius of 2.6 micron. You may further assume that due to tremendous flexibility of red blood cells, the wall concentration is 0.98. And to help you along the way, you can use the expression for flux that assumes a shear-enhanced diffusion as the back migration method. So they don't have the notes yet, right? So I'll have to give you that equation in a minute. We'll go back to that, okay? So I will give you this flux equation, okay? Actually, can I do it right? If I try to share now, can we come back to this, or will we lose it?
We can share.
Yeah, so I'll just share and then I'll come back to it. That's fine. So if I go back to my lecture here, here we are. It's this next slide. It's this one. So I need to just turn this off 1 second. Can you write this equation down then? Because this is what you need. You need that equation, okay? So this is due to shear-enhanced diffusion. I give you the red blood cell radius, right? I give you the length of the hollow fibers. I told you a wall concentration of 0.98 or something, and CB is what you've got to figure out, okay? That's the bulk concentration, okay? So that gives you the flux, right? So just one clue, if you're doing this mathematically, if this is the bulk concentration, your bulk concentration is changing, right? Because you want to go from 0.1 to 0.4. So you'll have to think how to use that equation if you want to go from 0.1 to 0.4. Because obviously if you put 0.1 here, you get a certain flux. If you put 0.4, you get a lower flux, okay? So what flux are you going to use? That's one point, okay? Let me go back to the problem now. So let's cancel this. And let me stop sharing. So was everyone able to copy down that equation? Because you need that equation. Sorry? Let me see.
No, that's okay.
Can you see it now? Or? Sorry, let me. Actually, they were going to get the slides, right? Okay. Maybe I should have just written it here. Is that big enough, or shall I try to write it? So it says that J equals 0.070 a to the 4th divided by L. Gamma W is the wall shear rate, which I give you, log CW divided by CB. Okay? So you do need that equation. Okay, everyone got it? Okay. All right, and then let me go back to the question. Okay, so going back to this question, you have actually 2,000 reciprocal, the wall shear rate, you know the radius of your red blood cells, you know the length of your module, you know the wall concentration, and so actually you know everything in that equation, but there's a small trick, and that is what are you going to use for your bulk concentration, okay? So that's the first part of the problem, is assume this, and a unit is to be concentrated. The concentration step must be completed in 10 minutes. The first part tells you you want to concentrate this from point 1 to point 4 in 10 minutes, okay? So how are you going to do it is the question, all right? So I'm giving you an expression here for the flux. So you've got the flux, if you can calculate that, and you figure out what to do. But then the flux is equal to what? Q divided by A divided by T, right? The amount you have to process, the membrane surface area, and time. You're told the time is 10 minutes. You really need to try and figure out what A is, and you need to figure out what Q is, but you know what J is, if you can calculate, okay? So that's the problem. Does everyone understand the problem, what you have to do here? Yes? Okay, good. Next, it says it is necessary to remove plasma proteins from the concentrated blood. In other words, the blood that has been concentrated to hematocrit here of 0.4. This can be done by diafiltering the blood using physiological saline. You have determined that a 3x diafiltration, in other words, this is 3 diavolumes, okay? 3x diafiltration means 3 diavolumes, 3 times your feed volume, okay? Is needed. 3 times the red blood cell volume after concentration is required for diafiltration. How much saline will be needed, and how long will it take to diafilter the blood? How long will the entire process, concentration and diafiltration, take? Okay. So I was thinking maybe the best thing is to let you guys work on that overnight, whenever you want, and we will talk about it tomorrow. So can you remind me? Tomorrow we have a lecture in the morning, right? So maybe we will start off tomorrow by doing this, asking you, we can work together to try and solve this problem tomorrow. We'll do that first, and then we will talk about membrane adsorbers, because this problem really brings us to the end of all the work that we're doing on pressure-driven, well, not quite, we've got virus filtration still, but most of it is done now in terms of pressure-driven filtration. So it's a nice problem, and it also leads you to blood processing, which is something we talk at the end. So is everyone clear what has to be done here? Because the problem is a little bit complex. So are you clear what has to be done? You've got a certain amount of, it could be any sort of feed, but this time it's red blood cells. You want to first concentrate it, and I'm asking you basically to do it in 10 minutes, right? It's to be done in 10 minutes. And so you have to figure out how much membrane area you need, okay? And then once you do that, you then say, well, now I want to remove plasma proteins. I'm doing a 3 times feed volume diafiltration, 3x diafiltration. But I know my membrane surface area now. So I do that, and then I'm saying how long does it take and how long does the entire process take, okay? Very good. Anyway, people who are engineers should know how to do the mathematics. If you don't, think of a qualitative way to solve it, okay? You won't have an exact numerical answer, but you can still tell me reasonably accurately what you think is going to happen, okay? So I think we'll stop at that then. And then tomorrow we'll pick it up from there, and we will talk after that about, I think tomorrow I'm talking about membrane adsorbers. Then we have a couple of guest lectures tomorrow. Actually, tomorrow is quite a lot, right? So so what we'll do tomorrow then, tomorrow is Wednesday, we'll have kind of like half a tutorial, and I'll start off on membrane adsorbers. I may not finish, but that's okay. I'll continue that during my second lecture, and then we have some stuff on virus filtration, and there'll be 2 other lectures as well tomorrow, okay? All right, thank you.